So short text analytics by Kai Larson, who is at CU. Very good.
That guy's so awesome.
I've heard that too. So at any rate.
And really funny.
I try so hard. So why do we care about whether texts are similar? Well, because things that are similar tend to denote that people or things that behave in the same way. So take this example here, right? Here's Justin's new cat, right? This jumps on him every morning. And it's like the cutest thing ever. Safe, 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 very cool. And if you have another one of them, you can pretty much assume they're going to behave the same way as well, right? So kind of fun to be around. They take care of you, all of that stuff. But then you introduce a real killer, right? This thing, I'm not a zoologist, but that looks pretty scary, right? And that should probably be able to eat you in no time sharp. So this is what we're dealing with here. When you have things that are similar, when you have people who are similar, they tend to express themselves in similar ways. And generally speaking, when you have large texts like this, it's no problem creating LSA spaces or LDA spaces that actually create good understanding of the underlying text and how it works. You know, Serena is closely connected to her uterus. And Erasmus, you know, if you're a Dune person, this is stuff you would be familiar with. But texts about the paragraph size or larger, you can dump all of that into LSA or LDA, and it's going to work great for you. No problem at all. However, if you have shorter text, like sentence or shorter, this stuff stops working all that well, okay? And the reason for it is simply that whereas you guys know that a car and an automobile is the same thing, right? You know that, right? So Google used to know that. Back in the days, you searched for a car on Google and not a single European car manufacturer would come up, okay? Because they didn't produce cars, they produced automobiles. Now, the reason why LDA and LSA works well with large text is that a car and an automobile are both things that have steering wheels, they have tires, they consume gas, they destroy our environment, right? So they're talked about in exactly the same way. But generally speaking, when you're at the sentence level, there's not enough of that additional text that gets in that you can actually draw the connections between words. So some general types of short text algorithms or text algorithms in general. I'm going to talk about a corpus models, knowledge-based models, and hybrid models, okay? And just quickly, a corpus model is basically you're dumping a bunch of text into a database and you're applying stats to it, okay? LSA, LDA, you create a semantic space in LSA, for example. Knowledge-based models, however, generally rely on careful human creation. 2 minutes? No way. I'm going over.
If they cheer for you, you can go over.
I'll beg when we get there. Oh, come on. That's nice. Knowledge-based models are based on lots of human labor to figure out which words are related to each other. Hybrid models combine these. So here's a corpus model, latent semantic analysis. Some of you may recognize Thomas Landauer of CU fame. In our project, we generally base this on small, by some of your standards, data sets, but they're very carefully created. So we analyze paragraphs, but paragraphs that are very focused on human behavior, for example, like what do CEOs do? You know, any newspaper article we can get about CEOs, we'll dump in there and create a semantic space that understands human behavior. Same essentially with LDA. So you do the same thing. LDA is a development further on LSA. And again, you dump paragraph stuff in, create your model, and then you project in sentences. Okay, so that's how you infuse your sentences with the knowledge of what words are actually related to each other. Word2Vec, another kind of LSA extension of Google fame. But this is basically LSA plus neural networks. And it doesn't work nearly as well as everyone loves to believe. Google Trigram, this is based on about 1 billion trigrams and 1 trillion total words from Google's web searches from 2006. Basically, you can get these massive files and look at how words belong together. If you look at the first and the third letter word of a trigram, you can figure out which words actually belong together. Alternatively, you have knowledge-based models, and they don't have nearly as cool names, but these are generally all based on, for example, WordNet that George Miller came up with. George Miller, a cognitive scientist of the magical number 7 plus minus 2 chunks of short-term memory. So these actually look at how far away are words from each other in this huge network of 40,000 words. So you both measure the depth, because the deeper words are more specific and the higher words are more specific, and width, how far away from each other are they through this network. And so we created one ourselves that sort of integrates LSA and Lee. It works really well for technology kind of problems. We found technology texts. But generally speaking, these days, we take all of these algorithms and we dump them into an extreme gradient boosted tree with early stopping rules. And at that point, you're able to actually work with 2 sentences like those and figure out that they're actually very similar. In spite of the fact that one talks about a leader, one talks about a boss, one talks about encouragement, and one talks about ridicule. So they are similar in that they're dealing with exactly the same sentiments, but opposite, right? Most of these approaches don't work at all for opposite. So they'll say these are really similar, even though they're opposite. We are currently testing a tool where we want to build in the APIs for people to be able to use these kinds of short text similarity approaches much more easily. And we're testing that right now with 4 LSA semantic spaces and me, but we're hoping to add all the rest. So if anyone's interested in being a beta tester or try it out, let me know afterwards. Thank you.
All right, who's got questions? I'm going to leave the heckler for second. Somebody else has to ask a question before me. Thank you, Steven.
So I'm working with Reddit text analysis right now. I'm scraping a bunch of subreddit data and trying to do some analysis. But in addition to looking at similarity, I want to look at topic modeling. Does what you're doing here relate to topic modeling or just document similarity?
We don't really care much about topic modeling, but one of the approaches actually creates a topic model and uses the topic vectors for 2 different sentences to compare their similarity. It's generally not the best approach, so I wouldn't recommend it as a starting point.
Have you heard of a new company called Viv?
I'm sorry?
Viv.
Viv, no.
It just got bought by Samsung, but it kind of uses a similar model to this. But the program itself rewrites its coding, and so every time it finds a new word, it rewrites it, and so it starts creating its own web. And so it's technically like going to be Samsung's new Siri, in which you can use it and it just keeps repeating itself. There's like a cool video online if you want to look at it. It's called VIV.
You should Slack me that.
All right.
Now, heckler colleague.
Wait, 2 seconds.
Oh.
I'm heckling him now.
Really?
So for the people on the web, that was Viv. Samsung bought it. It's going to be the new Siri. Okay. I turn the floor to Rick.
So your first assertion about similarity, could you explain that in a little more detail?
Which assertion was that?
Well,
I had many.
No, when you the very first assertion that you made, about
Similar things behave in similar ways.
yeah, similar
Yeah.
things, inferring similar.
Right. So, have you ever voted for someone who made racist slurs?
All the time.
And then have you looked over to the guy next to him and said, "Oh, that guy is also uttering similar racist slurs"? That might indicate that those two people have something in common. What we're finding actually is even things like if you like surveys, have you ever filled out a survey where you have to agree or disagree with something? We've actually found that with these methods, we can predict the whole correlation matrix of a survey of hundreds of people. Okay, so that's what all behavioral and social science is based on for those who do the psychometric approach. And these approaches, when you just do a similarity matrix based on the questions they ask, which are generally short, you can generally predict a huge chunk of the correlation matrix you get.
Okay, so what you're asserting is that your correlation values are as good or better than?
I'm trying to be very careful asserting anything right now. Right now we have a paper under review that finds that the top theory in my field is almost entirely text similarity driven. And to publish it, we're explaining very carefully that this is a sign of great strength for this theory, because otherwise it's not going to get published.
And this is going on YouTube, guys.
Other
Last
questions?
question.
Okay, thank you.
Thank you, guys.
We'll take it afterwards, so we'll be here.
Yeah, wait.
Oh, are you
No
sure?
We can wait or we can go now.
Let me jump in there.
Yeah.
Sure.
Okay, so I work in the chemistry field in biotechnology, and in chemistry, when we're looking at chemical similarity, we have a phenomenon that we like to call the magic method, which is two things that are very, very similar apart from, say, one carbon and three hydrogens, and they may have extremely different behaviors biologically. Do you see the same type of high similarity, high difference in functionality within the text-minded field? And if so, how do you deal with that?
Well, the most typical example of what you're referring to is that pesky little word not, right? You know, just that one word not will flip the whole meaning of something to the opposite, right? And these approaches don't work at all for that. So one of the things we generally do is that we, when we know which direction something, if we know something is negative, we'll turn it positive before we do anything with it, especially for survey correlations where you'll actually get a negative correlation in the survey, but you remove that not word and you would have gotten a positive correlation. So we do things like that. But yeah, I don't know a whole lot about chemistry, but I think we have similar problems.
Kai, can I posit that but is extremely important in your line of work?
I have no comment.
Thank you.
Thank you.
All right, up next we have Max Joseph, and I'll probably be just as rude to you. So come on.
That's all right. All right, cool. Hi, I'm Max, and today I'm going to tell you guys a story about two NBA players. One of them is Jerry Bird. He took one free throw in his career and made it. And then you probably heard of Larry Bird, who made about 88% of the 4,000 some free throws that he took. So which of these guys do you think is a better free throw shooter? Anyone? Jerry.
How many games do they have to play?
I think Jerry probably played one, maybe two. So we might go about answering this question using something like maximum likelihood, where we're trying to estimate the shooting ability of each player, which here I'm taking to mean the probability that they make a free throw by maximizing the probability of the data, or the likelihood. And if we do this, then our estimate for Jerry Bird is he has a probability 1 of making his free throw, which is to say he's incapable of missing free throws. And for Larry Bird, we conclude that he makes exactly that fraction, so his probability would be about 0.88. And if we do this for the entire collection of NBA players who've shot free throws since 1950, this is what we get. So the estimates are on the y-axis, and the sample size, or number of free throws attempted, is on the x-axis. From this, we conclude Jerry Bird basically always makes free throws, And somehow a large number of players managed to make it into the NBA that are completely incapable of making a free throw. That is, they have zero shooting ability, which seems weird. So an alternative would be to use something like Bayesian inference, where we assume that there's some prior population distribution of shooting ability across the entire collection of NBA players, parameterized maybe by a mean and a standard deviation. And each player, each of these stick figures, gets a shooting ability drawn from that distribution. Those players then take shots, which comprise the data, which tell us about the parameters for each player. And if we use this approach, this is how the graph changes. So now we would actually conclude that Jerry Bird was probably an average shooter, and Larry Bird's estimate hasn't really changed. Also notice that we're no longer inferring that players are completely incapable of making free throws, which seems a little bit more reasonable, right?
What?
Yeah. So we can also look at this with a slope chart. So here I've got the maximum likelihood estimates on the left side, our Bayesian estimates on the right side. Larry Bird, his estimate is shown in blue, and that line is basically flat, indicating that his estimate didn't change much. Compare that to Jerry Bird, who we went from estimating his probability of 1 to pretty much in the middle of that distribution. This is shrinkage. So we've shrunk Jerry Bird's estimate down to something that's more reasonable. So let's dig into this a little bit more. Looking at Larry Bird, I've got our prior distribution shown in red. So this is basically the distribution of skill across all NBA players. The likelihood we've seen before is sharply peaked around 0.88, and our Bayesian estimate is pretty much the same as the likelihood. Contrast that with Jerry Bird. The likelihood here you've seen before, the prior distribution is exactly the same, but our Bayesian estimate is pretty much the same as the prior, which is to say, we probably think that Jerry Bird was average in his free throw shooting ability, which seems a little more reasonable given that we only have one data point for this player. So what's going on? In this plot, I've got the maximum likelihood estimates on the x-axis and our Bayesian estimates on the y-axis. Shrinkage shows up in this space as vertical distance between the points and the dashed lines. The estimates that are shrunk the most are those for players who took few shots, which is basically dark colors, and players whose maximum likelihood estimates were far from the league mean. So here, Larry Bird is that blue dot, which is basically right on the diagonal. His estimate's pretty much the same. We didn't really shrink his estimate. Jerry Bird is in red. His estimate was shrunk downwards. So once you start kind of recognizing what shrinkage is, you'll see it all over sports media coverage. How many of you guys watch the World Series?
Boom.
Okay. So every time a player goes up to bat, the sportscaster tells you what their World Series batting average is, as if it's some indication as to whether they're going to hit the ball, right? Well, we can evaluate that idea with data. So I'm going to show you the World Series batting average on the x-axis versus career batting average for all Major League Baseball players who have made it to the World Series since 1908. And if players bat similarly in the World Series compared to the rest of the season, you'd expect that most of these points should be along this one-to-one diagonal line. But here's what the data actually look like, right? So there seems to be little correspondence between the batting averages in the World Series and the batting averages the rest of the season. So what's going on here? Well, one thing to remember is that players actually have far fewer at-bats in the World Series than they do the rest of the time. So these World Series batting averages are being generated from extremely small sample sizes. As such, they probably provide a pretty poor indicator of the probability that a player is actually going to hit the ball in the World Series, which sounds weird, right? If we wanted to actually go from a batting average to a probability, we would probably want to shrink these estimates, which is basically to say combine it with other information, prior information, which is an inherently Bayesian thing to do. So what? So once you start thinking about shrinkage, you'll hear a lot of bizarre sounding, kind of cutesy, but ultimately bogus small sample statistics in sports. That's kind of annoying, but I think the really cool thing is I can show you guys these data, and in your head, without actually applying any formal mathematics, you can reason that Larry Bird was probably a better shooter than Jerry Bird. And I think that brings up some interesting questions about the extent to which we can innately apply something like Bayesian inference without actually having to do the math using the theorem. Thanks. All the data and code are available. I'll take any questions.
Woohoo! I'm gonna let Rick
Jerry, if he'd done 4 out of 4, or 8 out of 9, or 99 out of 100, where's the threshold that it starts to make a difference, right? That for comparison. And the other side of that question is, when do I want to just chuck the 1 for 1, chuck the too small sample cup?
Yeah, so that's a good question. So your first question we can answer by looking at this
Can you
plot.
repeat the question really quickly?
Oh yeah, so the question is, there's a two-part question. The first is, at what number of free throws can we actually start to reliably use the information on their empirical shooting proportions? And second, does it make sense just to discard all of the information below some threshold? So to answer the first question, it's actually kind of a continuous gradient of the amount of trust, which is essentially how much does the estimate get shrunk as players shoot more free throws. So in this plot, along the diagonal, those are players who have shot tons and tons of free throws. Like Karl Malone, for instance, has taken the most free throws in the history of the NBA because he got fouled a lot. So players who get fouled a ton, their estimates are identical. But it's basically a continuous gradient from that to small numbers.
But you said you can intuit, when the Bayesian is a good tool to use. And I want to kind of refine that intuition. Like, okay, so I'm comparing these two things. I know some guy shot a bazillion.
Yeah, okay.
I know some guy shot 10. Is that good enough? Or shot 100? What's good enough?
So here's basically what's happening. So Bayes' theorem tells you the probability of parameters given the data. And it shows basically that that's proportional to the likelihood, probability of the data given the parameters times the prior. Yep. Okay, so typically we have lots of data points, and we're treating those as independent. So if we've got n data points, this would be the likelihood for each of those data points given the parameters times the prior distribution. And so if you can think about this in log space, basically we've got the sum of the log of the likelihood for each of our observations given the parameters plus the log of our prior distribution. And this sum goes from 1 to n. So as n gets really large, which is to say players take lots of shots, this sum is actually dominating the posterior distribution, and the prior essentially has no impact. If players are taking few shots, you're adding, for the case of Jerry Bird, 1 piece from the likelihood to 1 piece from the prior, and the prior is more influential.
Yeah, so you're essentially saying if you've got a factor of 100 difference in these things, throw it away. Right?
Yeah, you can, and that's what the NBA does. So when the NBA ranks shooters based on their ability, they discard any players who have shot less than some amount. And who knows how they come up with that amount? It varies by season.
But if you do it like this, if you take the logs and say, hey, look, the difference between the two elements that you're summing is bigger than, say, 10, screw it.
You could do that. I prefer to just build a full Bayesian model and propagate forward all the uncertainty so I can make inference even if we have players who have taken only 1 shot, or even players who didn't even get to take a shot. Good question.
Do we have any questions from people on the web? If so, go ahead, let me know. Anyone in the audience?
Yep.
Wouldn't a better prior for Jerry be his college free throw shooter?
Absolutely. So there are lots of sort of places you can glean prior information from. And presumably the more prior information you bring in, the better your estimate should be. So yeah, Jerry, the picture I showed, he is playing college basketball. So this model doesn't include any of that information, but you could in principle.
All right, our last question. Max isn't scary, ask him a question.
Yep.
Have you thought about taking this model and this type of thinking to anyone in the NBA or in college basketball? I'm serious.
Not really. So I study spatial statistics and spatiotemporal models. This is just kind of something I do for fun, but you could in principle. So because if you do apply this model, the inferences that the NBA makes on who's the best player actually changes. And the nice thing is, instead of just coming up with a discrete ranking, which they currently have, you can actually probabilistically evaluate who is probably the best shooter in the history of the league, which I think is probably more informative.
Max, you're going to make some money in online
Oh yeah.
game sports.
So yes, FanDuel sports gambling. If you guys do that and you're
gonna make
choosing
some money.
players, you can do this pretty easily. So all the code is free. Feel free to use it. If you make money, buy me a beer.
I know. And Tony, I know how we can fund the beer.
Yes! Awesome, thank you.
Cool.